If you guys have ever been to an amusement park, see the ride, the Gravitron. That's the one where you end up sticking to the wall as this thing rotates around. It only happens when they rotate around a certain speed. So it's a very interesting problem here. And so, you know, you're going around the Gravitron, and once they get it up to the speed, then you stick to the wall. So what's happening is that when they end up spinning it, there's got to be a force that causes you to move in a circle, and it's a normal force acting on you pointed towards the center. It's the wall pushing on your back the entire time. This simulates gravity in this direction against the wall, or in this direction for this person against the wall. Their simulated gravity is always opposite your normal force, essentially. And then when you look at this, you still actually have the true force of gravity acting on you from the Earth right now. Looking at those two vectors, it doesn't really make sense as to why you would stick to the wall. But if you have a normal force present, that means there has to be a force of static friction present. So we're going to write F of S max in the upward direction. And what ends up happening is that if your normal force is large enough, you get a large enough force of friction, and that prevents you from sliding because it can balance out the force of gravity. So we'll have no motion in the y direction. F of S max will be up. Gravity will be down, which means that F of S max has to equal the force of gravity. And then I'm going to leave myself a little bit of space there. Look at the x direction. The x direction, that's where we have the motion. It's a horizontal circle. So mv squared over r, and our only force in the x direction is n. Now if we go back to this, it's mu Sn equals mg. And I can take this expression and put it right in there for n. And what I find is that, well, when you look at this, you know, it's the higher you, the faster you spin, the larger your normal force is. So it kind of makes sense as to why you would get more friction and enough to stick against the wall. But let's put that in there. We get mu s mv squared over r equals mg. You may notice that all riders in the Gravitron, regardless of how large they are, stick at the same time. Mass cancels out here. And then if we wanted to solve for v, I would divide both sides by mu and also multiply both sides by r. So we would get that, and then we'd finally square root. And then this is the minimum speed needed for you to stick to the wall in this particular ride. And it's called the Gravitron because it simulates gravity. Spin it fast enough, your apparent weight, which is this value n here, it's quite large, and you feel like you're almost glued to the wall because it's so strong. Now, the reason they call it a Gravitron is literally because it simulates gravity, and they will do that in space as well. So here's one of the weird things about space that, you know, people have misconceptions with. If you're up here and you're in a spaceship, a lot of people think you're at zero gravity there, but you're not. You know, the Earth is right here, and it is pulling down on this with a force of gravity. You're only in an environment that simulates zero gravity. But if you've ever watched let's say a movie where they magically somehow like turn the gravity on in the spaceship or the space station, there's something they have to do to accomplish this. So if you were talking about a space station, the conventional design for a space station is literally, it's a donut. That's an awful looking donut. Let me make the donut a little bit better. And what they'll do is they'll spin it, and spinning it will simulate gravity, essentially. But what ends up happening is just like the Gravitron, you'll stick to the wall. But you got your person here, and then all of a sudden, the normal force will start to act on them. And then, if there was a person here, the normal force would act on them from this wall. Now, a lot of people look at this force, and they'll go, well, why doesn't that actually push them, cause them to move towards the center? And you got to realize they're moving. If I had like a door here that I open, this person would go flying right out of there tangentially. So the normal force only redirects their motion. And then what ends up happening is that it simulates gravity very nicely, because this person can walk along the whole outer edge as if it's the floor, and then this inner ring, the top of it, that's the ceiling. So that's how they essentially simulate gravity, and it's a very simple problem to model because sigma F equals mv squared over r. The only force that we can see acting on the person is N. And if we want them to feel just like they are on Earth, we just set N equal to mg, where g would be 9.81. And if you did that, the speed that we would need to rotate at would be, let me put an mg there. You cross out m, you solve for v, you get radical gr. That appears over and over again in this unit. So that's basically how a space station would work.